Okay, here we are at part 2 of lesson 1. We are talking about average versus instantaneous rate of change. We're looking at secant versus tangent lines. Alright, so the magic all occurs here. Let's see. There. The magic, let's move that over. All the magic is occurring here at A. So we're going to put a point at A. There are two things we're looking at. If I draw a line that goes through the curve and then intersects the curve again, then that is not a tangent line, but a secant line. Here we go. Now I made it a line. And the slope of that line has some significance. This value here, now this can change and is random, but for this first drawing, I'm going to make it a fixed value of b. The slope of this line represents the average rate of change, in f on the interval x equals a to x equals b inclusive. So the slope of that line is very important. It gives us an average rate of change. You can see if the only thing we're looking at is the purple line, then the slope never changes. The slope is always m, and the average rate of change is that value of m. But in the yellow curve, the rate of change is constantly changing, but the slope of the purple line connecting these two endpoints gives us the average rate of change. Now if I write that as a mathematical expression, m equals f of b minus f of a all over b minus a. You might think of that as change in y over change in x. So let's come down to the drawing beneath it. Again, we have our magical point at A, and I'm going to try to replicate the same picture. Let's extend that a little bit further. The difference in this drawing is that this point here, we're going to say varies. So it gets the value of x. I could have drawn it here, here, any point along, I could have drawn it. And again, that is a secant line. Here we would say m equals f of x minus f of a all over x minus a. That's if x is allowed to vary and not fixed as it is in the first illustration. Okay, again, that is the secant line. Okay, so what is calculus? Calculus is a study of rates of change, and one of the things that we look at is in fact, the primary thing we look at is what is an instantaneous rate of change. So at this value of a, again, the word at this value of a, I am interested in what is the instantaneous rate of change. What is the slope of the yellow curve at that white point? That can be represented with a tangent line. Slow and steady. So that line is tangent to the yellow, and that is m. And the question becomes, how do we come up with a formula for the m? I mean, this is what calculus is. The first part of it, at least, derivatives, talks about what is the slope of the curve at a point, and it's equivalent to what is the slope of the tangent to the curve at that point. So what I'm asking you to think about, and hopefully you see, or maybe you've learned this already in another course, is the purple has to be pushed down or scooted over in order to make purple equal to red. So the question is, how do we mathematically make purple equal to red? And the only way we can do that is with a limit statement. And so we would say here that the slope of the tangent line is the limit as x is approaching a of this expression f of x minus f of a all over x minus a, provided it exists. Okay? Now mathematicians want to look at this in another way. Instead of calling this x a varying point, let's call the distance from the fixed a to the value of the varying x, let's call that change in x, or some authors like to use h instead of change in x. So that is a distance. It is a varying distance. It's going to give us another way to approach the slope of the tangent line. So let's take a look at the secant line again. Let's use the purple so we don't get confused. Okay. So the secant line, this purple slope line, it can be expressed instead of x, we can use it in terms of h. So this is going to be f of the a plus the change in x minus f at a. So instead of saying f of x, we're saying f of a plus h. And then on the bottom, the x minus a, well, it becomes a plus h minus a. And the a's cancel out. So we have f of a plus h minus f of a all over h. That gives us an expression for the secant line's slope. Now the slope of the tangent, which is ultimately what we're looking for, instantaneous rate of change, the slope of the tangent, can be written as another limit statement, f of a plus h minus f of a all over h. Again, that's the secant expression with a limit. Can you see what the limit statement will be? It will be that change in x is going to 0, or this distance that we're calling h is collapsing. So the limit as h goes to 0 of this ratio is the slope of the tangent, again, provided that it exists. And that is what calculus is, the derivative is. So let me put a little sloppy box around this. So what does this box represent? It represents the instantaneous rate of change of a function at a particular value of a. It also represents the slope of the tangent to that curve at that particular value of a. We give this a name. We call those things the derivative of the function at x equals a. Again, that is the derivative of f of x at x equals a. If asked what is the definition for the derivative of f of x at x equals a, I would state one of the two in this box. You see we have two here. The top one is actually considered the alternate definition, and the bottom one is considered the standard definition. Now, depending on the circumstance, as you will see, we can use the alternate or the standard. Example number 1, if you're following along in the notes packet, example number 1, y equals f of x, and f is defined as 3x squared minus 2. Part A wants to know, find the slope of the tangent line to the graph of x, to the graph of f of x at x equals 1. Find the slope of the tangent to the graph at x equals 1. Another way to say that is, what is the derivative of f at x equals 1? Now that's a mouthful, so different mathematicians have come up with notations to say what is the derivative of f at 1. So if I use a little prime here, f prime of 1, that says the mouthful precisely and concisely. f prime of 1 is the derivative of f at 1. And this is what's considered Lagrange notation using these primes. We'll investigate some other notations later. So f prime of 1 equals the limit as h goes to 0 of f of a. In this case, our a is equal to 1. So f of a, 1 plus h minus f of 1 all over h, which equals the limit as h goes to 0. Now I'm going to plug 1 plus h into the expression. So I have 1 plus h squared minus 2 as like that. And then f of 1 is f of 1, which is 3 times 1 squared minus 2 all over h. Now we're going to do a little bit of algebra simplification. This is the limit as h approaches 0, and this will be 3. Now I'm expanding this expression here and then distributing all in one step. So we have 3 plus 6h plus 3h squared minus 2 minus, if I simplify inside the bracket, I get 1 all over h. Okay, we're going to continue simplifying. This is the limit as h goes to 0. 3h times 2 plus h. See, the 3 cancels out with the 2 and negative 1. And I factored out a 3h. And we still have over h, which simplifies further. The limit h goes to 0 of 3 times 2 plus h. Now I'm able to plug in h is 0, and I get the quantity of 6. That tells me 3 things. The instantaneous rate of change of the function f at 1 is equal to 6. The slope of the tangent to the function f at 1 is 6. Finally, the derivative of f at 1 is 6. In part B, they're asking to come up with the equation of that tangent line. Let me give you a little real quick sketch here. So here's the parabola, real rough sketch, looks like that. And at 1, we're going to have a tangent line, and that tangent line is going to look something like, oh, that's bad, but here's the point. And we found that that slope is equal to 6. And in part B, we want not the slope, we know the slope is 6, we want the equation of that tangent line. I prefer to use point slope. Y minus y1, it has some utility later, equals m, x minus x1, point slope. And so let's write this a little bit more descriptive. Instead of y1, let's say f at a. Instead of m, we learned that m is f prime of a, and then x1 is the point, the x coordinate, which is the a. So this is a better version of the point slope. And let's plug in what we have. So y minus f at 1 is 1. F prime of 1 is 6, x minus 1. And there we go. That's because it passes through the point 1, 1, which makes this drawing really bad. So it's more like here, and the tangent line is here. Slope equals 6, because that has to pass through 1, 1. 1 or 1, 1. Other notations, let's say f prime of 1 equals 6. That's Lagrange. There's another mathematician, Leibniz, dy dx with a slash, which means at x equals 1 is equal to 6. We also have Newtonian, y with a dot above it, that means one single prime. y at 1 equals 6. And then we also have Euler, who says the derivative of f at 1 equals 6. In this course we use Lagrange and Leibniz. Okay, let's go to example 2. It gives us a function s of t equals 5t. Wants us to find two things: the average rate of change on 0 to 4 and the instantaneous rate of change at x equals 3. So here, this is just a change in y over change in x, or change in s over change in t. So this is going to give us s at 4 minus s at 0, all over 4 minus 0, which gives us 20 minus 0 over 4, which gives us 5, and that's some unit per some unit of time. Let's just say hours, or units per hour. Now the instantaneous rate of change, then, we can denote it as s prime of 3, and that's going to be the limit. Now I'm going to use the alternate definition here. We're going to mix these up a little bit. Now t is the variable, so it's as t approaches 3 of s of t minus s of 3 all over t minus 3, which gives us the limit as t goes to 3 of 5t minus 15 over t minus 3, which then equals the limit as t approaches 3, factoring out of 5, we have t minus 3 over t minus 3, gives us the limit as t approaches 3 of 5, a constant, which equals 5, again, units per, let's say, hour. A little bit of common sense tells you this makes perfect sense. It's a no-brainer. So here's a function. If this is t and this is s, then we have a linear function, 5t, and the average rate of change will always equal any instantaneous rate of change, because that's what a line is, a constant slope. Example 3 wants the same thing. It wants an average rate of change, in this case on 0 to 8, versus the instantaneous rate of change at 3. So the average rate of change, s of 8 minus s of 0 all over 8 minus 0, is going to give us 3 minus 1 over 8, or 2/8, simplify 1/4. The instantaneous rate change at t equals 3. Let's use notation. So s prime at 3. Again, I'm using alternate definition here. The limit as t approaches 3, s of t minus s of 3 all over t minus 3. And let's do some plugging in here. So that's going to give us the limit as t goes to 3, the square root of t plus 1 minus 2 over t minus 3. And this is getting a little sloppy here. Okay, now how do we do this limit? We can't simply plug in the 3 because we can't plug it in the denominator, so we need some trickery. And if you want to press pause and think about it for a minute, that might be cool. Otherwise, you might recognize you need to multiply top and bottom by the conjugate of the numerator, like that. Top and bottom by the square root of t plus 1, then plus 2, that quantity. When we do that, now I gotta keep writing these limit statements. As much as they can be a pain, it's important. I'm going to expand or FOIL the top. The radicals disappear, so we have t plus 1, and then that's going to be minus 4. I do not want to touch the denominator. That would get really messy, so I'm going to leave that alone. oops, t plus 1 plus 2. We'll leave that alone. And then you hopefully can start to see this, that the top goes to t minus 3. And then in the bottom we have this t minus 3 times t plus 1 plus 2 quantity, like that. So these will cancel out. And let's see if I can't sneak that in here. The limit as t goes to 3 now of 1 over the square root of t plus 1 plus 2. Let's extend that. And now I'm permitted to plug the 3 into the t, and that's going to give me 1 over 4. So the question is, the average rate of change was 1/4, and then we found the instantaneous rate of change to be 1/4. If you really follow along, you'd be able to answer this question. Is that a coincidence? And the answer is yes, a total and complete coincidence. It's actually a bad example by the fact that it makes you feel like it's not a coincidence. It is a coincidence because this function, let's see, it's gonna shift over like this. Okay, and that's the radical function, but we're looking at it between 0 and 8. So the average rate of change is the line connecting these two endpoints, a very sloppy line. And of all the points it could have possibly picked, 1, 2, 3, 4, 5, 6, 7, or 8, of all the points, I just so happened to pick the one where the instantaneous rate of change, the slope of this green, is equal to the slope of that pink. Had I picked any other point, in other words, had I said s prime of 1, well, that certainly would not have equaled 1/4, or s prime of 5 would not equal 1/4. There was only one point that I could have picked, and that was 3, where the instantaneous rate of change equaled the average rate of change, because it is constantly, the slope of that tangent is always changing. So coincidence? I think not. That is the end of part 2.